Hello everybody. Yeah, just this is part 2 of a video that's dealing with this MSCIEN 4-way mains adapter extension 10 amp with power cutout or a current overload trip with the 3 USB and USB-C charging ports. The problem with it is that the charging ports have gone. Part 1 of the video, which is another video previous to this one, is dealing with just running over this very simple board, an evaluation of it, talking about the technology, what's on there, and some other information. And this video deals with the troubleshooting in detail of this board with data sheets and circuit diagrams and oscilloscopes. And the third part is the actual comparison between what they're shipping now and what they shipped before. We've just purchased a couple of new ones just to see if they've improved or they're equally as bad. So yeah, this is part 2, the diagnostics and fault finding and repair. So yeah, thanks for watching, and stand by, here we go. Okay, let's have a quick look at this board, close up and personal. There she is in all her glory. There it is. Should I turn it around? I think no, the legends are up the right way, so let's just back out slightly. Backing up. Beep beep beep. Right, pointy thing, tweezers. Right, so what have we got? We've got the mains input just here, which I just then soldered. There's a neutral and the live, and then where it comes in, you've got a 33 ohm resistor in series with the live. So the live comes in, and incidentally this is probably a fusible resistor. It isn't a straightforward 33 ohmer. If you put a standard 33 ohm in there, wire wound or otherwise, you'd end up with a firework. But these have got some sort of compound inside which causes them to kind of explode and crack open. So it's a fusible safety resistor, a fuse and an inrush limiting resistor, all in the same package. So don't get confused when you're swapping these things out. I'll do a demo one day just to show you the difference between the two. One's a big pile of ashes where your house used to be. The other one's a crack and a bang and a little flash and a puff of smoke and a dead appliance. So it's your choice. Right, so anyway, what we got? It comes in here, through there, goes through this bridge rectifier, AC in, DC out. We'll call this AC 0 volts. It's not related to the neutral, but we'll call it AC 0 volts, okay, and AC B plus if you like, which is the on UK mains at 240 volts AC input. You'll end up with about 350 360 volts DC. It's obviously 100 hertz rippling. There's a ripple suppression capacitor or reservoir capacitor, 400 volts, 6.8 microfarads. No sign of doming on the can. No sign of doming on the can of any of these. That's a surefire giveaway. Always look at your boards before you start poking around with a meter, because you can slight convex evidence of pressure within this capacitor would indicate that it's not very happy. And being a cheap Chinese capacitor and being subjected to rectified mains, they, given their due, they have put a 400 volt capacitor in. Quite often it's 350, which isn't enough. Anyway, so there it is. It seems okay. It's been alright. This isn't that old. This here thing is about 18 months old when it blew it up. Anyway, so you got your so let's zoom out. Well, no, stay there actually. Let's stay there. You can see you've got a couple of whatever they are, 470 microfarad, 470 microfarad, 16 volts. Now I don't understand that. Why would you use a 16 volt capacitor on a 5 volt rail? This is a DC decoupling capacitor of the secondary side of the system, which is supposed to smooth the ripples and provide a reservoir and low impedance, relatively low impedance at lowish frequencies for the supply for these charging sockets to go off to their various devices to which it is being applied. Now, why 16? Now, when I was at university, our electrical engineering guy, lecturer, Mr. Brown, said, oh, you know, you mustn't put capacitors. Don't think that putting double the voltage makes it twice as reliable, the electrolytic capacitors, because the voltage rating of the capacitor is designed so that it stays well polarized at the operating voltage. So the chemistry and the etching on the aluminium plates differs. And I've seen this consistently whenever I see a circuit and I think, oh look, there's 1.7 volts across that capacitor and it's a 12 or 14 volt, 16 volt capacitor. You know that the capacitance in that device will have ebbed away to zero. It's still true. It's not really understood, but I can assure you it is true, because I've seen it on endless things I've fixed where a capacitor that's rated at, say, 50 volts is only running at 6 or 10 volts, and you know, oh, I bet that capacitor's shot, and sure enough they usually are, and often that is the root cause of the problem. So rate your voltage on your capacitors wisely. Don't think putting twice the voltage capacitor into the circuit is going to make it any more reliable than one that's rated for that working voltage. Alright, good tip, you heard it here first. Anyway, so what we got? We've got this these smoothers here, nice and smooth, and then we've got your USB-C and then USB-A sockets. You've got class Y capacitor connecting the 0 volts on here to the AC 0 volt line, which is the rectified DC line, which is not at neutral potential. Study your bridge rectifiers and you will understand. And then down here we've got another class Y capacitor, might be the one in the primary snubber circuit, and a bobbin wound switching transformer which has got one winding over the other. It's okay if they're double insulated. On a microwave transformer you'd have a plastic separator, and the primary would be wound on one side, and then the other side of the bobbin would have the secondary on, i.e. the low voltage secondary in this case. Obviously not a low voltage secondary on a microwave, but you get the idea. You get separation, physical separation, rather than just relying on the insulated layers here, because if these layers short out you could get mains voltage on here. Spoil your day. Now I turn her over to the back side, which is all the best way. What have we got here? What have we got here? What have we got? Ding ding ding. Right, can you see that? Can you read that? I can just about read it with these glasses on. Yeah, so we've got that one I think is a U6513BS, that one. That isn't the diode. I'll talk about that in a minute. So that's another chip. And this one's this one is the PWM management chip. So it's a pulse width modulated power supply chip with feedback and a integrated switching FET. This is the snubber network for the diode, for the primary of the transformer. The primary transformer is connected to there, I think. Then you've got this insulation gap, because often when you've got a pin in there you can get tracking on moisture, so a little bit of moisture would make this flash over or leak or corrode away at itself. Generally not be very good at all. So when I design these boards, when you have a chip with a missing leg, you usually mill a slot in the board to stop surface tracking. When it gets moist, if you get some condensation, it's game over basically. There's no conformal coating on this thing. It wouldn't be good in a a dew point crossing environment where you could potentially get condensation on the board. So you've got your snubber network and that capacitor, that diode and that capacitor is across the primary of the transformer. It's a snubber to calm down the overshoot when the back EMF is generated and direct it through the secondary winding. Now you've got a low, let's see if we can do something with this. So in the middle there, if I just raise this up slightly so you can get a somewhat better look at it. Well, that's focusing thing. Yeah, so yeah, that's upside down. I'm going to turn it around so you can read the numbers. you've got R820, so it's a 0.82, a 0.82 or 820 milliohm resistor, and that you always find a low voltage or a low value resistor in the circuit in one of these power supplies, because that resistor is in series with the 0 volt line or the AC 0 volt line of the switching FET. So this resistor is passing the current that's passing through the primary. When you switch the primary, you get a spike of current on this resistor. The current generates a small voltage, usually between 3 and 400 millivolts, and the chip is using the voltage generated across this resistor here to monitor the primary current. So if there was a short circuit or a blown something on the secondary circuit, when this thing fires up and starts switching, even on the first pulse, if there's an overload of the FET, it's not happy. It will shut the FET off mid switching cycle and stop the chip from damaging, or the whole thing from brewing up. Now if you see these low value resistors in circuit and they've exploded or open circuit, but you should always test them, because sometimes they go to a weird value and you have no idea until you measure it with your meter. And when the FET goes short or this fails, have a catastrophic failure inside the PWM circuit, your low value resistor will often get blown open circuit. And if you put a new chip in and don't notice that and don't check that, then when it fires up again, you're going to get very low, either if it's just drifted out slightly, you're going to get very low current capability or strange behavior from the power supply, and if it's sufficiently badly damaged, it can blow up your chip, because the FET leg is now being pulled higher than the electronics in the VCC for this thing. So check your low value. It could be anything from 0.1 ohm up to an ohm probably, but it's the only reason for having a really low value resistor in the switching circuit. On the high side, which is where this side is all high side, that's all mains, and the other side is a low side, which is on the secondary of the transformer, is the safe, supposedly safe delineation between what's accessible to the user, i.e. your USB plug, the 0 volts on the USB plug, and what's actually connected to the mains and operating at mains potential. So any kind of failure on this side could have mains anywhere on this side, but the idea is that it's blocked by the insulation between the primary and secondary in the transformer, and in theory the only coupling to the secondary is via the magnetic field in the core. There is some capacitive coupling which we can talk about some other time, but the significant one is the magnetic coupling. So you can see, unless the insulation in here breaks down or you get some kind of a short or condensation, you should be relatively safe, although this isn't really adequate separation for, especially here, for the high to low side, the AC high voltage side and the DC low voltage safe side. This isn't really adequate. I could put it on the Schaffner and try it at 2 kV and see what happens, but the slightest bit of moisture and that will track across there. I know from experience from doing approved products, design of. Well, that's your board. Anyway, so what have we got here? So we've got the primary side here, and we've got the 305 300k resistor, which is powered from the B plus AC B plus. So 360 volts on one end, and it's a very low current path down to this here capacitor, which is the bootstrap reservoir capacitor. It sounds good, doesn't it? Bootstraps. 10 microfarad, 50 volts. So I've done it again. It's not going to get 50 volts on it. So when you put the power on, this capacitor charges up through this resistor, and the voltage builds up until it gets to about probably 17 volts. At which point the switching chip detects that you've got the 17 volts on your capacitor, and it will start the power supply. Okay, get running. Now this resistor here will not provide enough juice or power, because of the high value, to power this chip permanently. When it first fires up, this chip is running from the stored charge in this reservoir capacitor. Right, so what do you do when it's running? You get that initial kick, the thing starts up, and then from the secondary, from another winding on here, there's a low voltage winding on the primary side, the high voltage side of this transformer, which goes through this diode here into the capacitor, and that diode there is the rectifier diode for the bootstrap. So it's called a bootstrap. It's like pulling yourself up by your own bootstraps. You've heard that. It's the DC VCC power supply for this circuit to run when the power supply has first started. Of course, when it tries to start up first time, there's an overload or something like that, the capacitor juice will soon run out. There'll be nothing. No, the cavalry won't arrive across this diode from the primary when it's running to keep this powered up. So the voltage in this capacitor will just ramp down, and then at a certain point, this thing will shut down. So you get this pulsing starting and then failing, starting, then failing, starting, then failing thing going on. Okay. Now look at the secondary side. This is quite innovative, really. I mean, we've got 2.4 amps. So it's nearly like a 12 watt supply or something like that. 12, 13 watt supply there will have you believe. We can check it to see if it is. But normally in the old days you used to have just a plain diode across there, plain silicone. A lot of people put Schottky diodes in, but honestly they don't last. Number of Schottky diode rectifiers in the secondary side on power supplies that I've changed. When you go in there, they're just short circuit. So Schottky is not good. It has to be a rapidly switching diode because it's running at probably 50 or 70 or 100 kilohertz, this thing. So you need a rapid recovery diode, a fast silicon rectifier. But the problem with the silicon rectifiers is Schottky might have maybe 0.4 volts across it, but at full current a silicon rectifier diode would probably have 0.7 volts. So if you've got, you know, the equivalent of 2 amps going through 0.7 volts, you've got almost like 2 watts of power being lost in the rectifier diode. And anyone that's worked on power supplies will realise that the rectifier diode gets quite toasty when you start to give it a load, a big load. Give it the full load. It's the only way to do it. Anyway, so this is a smart rectifier chip. They first appeared maybe 5-6 years ago. There's an FET in there and a switching circuit, and when it detects the input to the from the transformer winding goes above a certain voltage sufficient to drive the secondary side, it turns the FET on, and then in which case you've got an equivalent channel resistance of maybe 50 milliohms or 20 milliohms, much more efficient. This will run much cooler because there's no heating due to the band gap resistive loss in the diode. Okay, basically it acts just like a resistor. Or does it? Think about that. Semiconductor resistor, what do you think? Comments in the comments section. I'd be interested to know what you think. Anyway, this is a rectifier, precision rectifier chip. It's a U6513BS 3BS, and there it is. And that on the outside, on the other side of that, so that's acting as a fast switching lossless diode, if you call it, almost like a perfect diode, if you want to call it that, an emulation of a perfect diode. Goes through to this side, and that point there should be the 5 volts to supply all this gubbins up here, but it's not working. So the question is for you guys, place your bets. Why is this not working? It's a simple circuit, minimalist. I think I've got some of those chips. They're about 15 cents each of those two. They're Chinese chips. They don't have UK data sheets because we don't really need to know. But if you buy a chip like that in the UK, it would be nearer to a 70p, I should think, rather than 15-20 cents, right? So there they are. There's a rectifier could be blown. The switch mode power supply chip could be blown. We could have, the other problem with this is that because we've got this, I just mentioned this here, we've got 330k resistor, or 300k resistor. Clearly if this capacitor becomes leaky and the DC path starts to get significant in relation to this, then it may well measure the capacitance, but if it's leaky, i.e. there's a DC parasitic loss, resistance loss across the electrolyte, then this may never charge up. And being a 50 volt device, being used run at 7, also the capacitance could ebb away to 0. So always take this component out and measure the leakage, and also measure the capacitance to make sure it's correct, alright, because that will cause things like intermittent startup and not starting up and all sorts of strange things going on. So that cap has to be good. This diode obviously has to be good. That resistor there has to be good. In fact, all the components need to be good pretty much. You get the snubber diode sometimes shorting, especially if they've used a Schottky one, and you get the you can get the rectifier diode for the bootstrap supply going short, especially if they've used a Schottky one. I don't know what it is about Schottky. There may be reliable Schottkys out there, but I always, when I get a design, I thought, I'm not going to put a Schottky in there. I'd rather use one of these things, one of the emulated perfect diodes, if you like. Right, so let's set about finding out what's wrong. I've got some of those chips. I've got all sorts of different chips. If you've got one of these and you want to fix it, I've got loads of these in stock, so I'll just put some in an envelope, and for a small consideration, just for a little bit of time and postage, I can send them to you, because it'll be cheaper than you can get anywhere else, I should think. Not that I'm in business to do that, but we do have an office which is doing daily shipping, so you know, you can capitalize on that as a, a faithful YouTube channel follower. Right, so where to go on this? So I'm just going to buzz around this for a minute just to see what we've got here. I'm not sure you can see this at all because of the light. Right, we're just going to do a bit of probing. Not the UFO kind, just a straightforward healthy probing. Zoom out a bit though, aren't I used to have a separate camera set up for this, but what the hell. I'm going to put it on continuity to start with. Okay, so we short the probes together, we get 1 ohm, all the voltage. This is a weird setup on this meter. So diode number 1. This is the snubber diode. Is it shorted? No connection that way. If I swap the probes around, then I should get. So that's a silicon high-speed silicon switching diode. They've got 0.6 volt drops on diode forward voltage drop. That's a good diode, right? The next diode is the the bootstrap supply diode. I've got 0.6 one way, an open circuit the other. That's good. So we've got, put it onto ohms now. We're going to check the 0.82 ohm resistor. 1.2. If I just do the probes like that, I get 0.4. Okay, so that's 0.8. Got that? Well, it says 1.1. Yeah, 1.3. There you go. 0.8. So that resistor is good. That's good. Is this diode shorted to ground? We'll check the output side of the unit, which is across these two caps. Caps. And the negative of the ground, I think, or the 0 volt rail, is this one. Yeah, it is. So to there is those caps. And you can see the voltage rising as the capacitor charges from the diode forward voltage drop voltage supply, and it's not that low, but it's gone up to kilo ohms. Actually, we're on ohms at the moment, so it's been charged from the that's pretty low, actually, pretty low. That one the same. Not sure. And a kilo ohm wouldn't do it, would it? Seems pretty low. Let's just check this device. I'm guessing this one's going to have basically the anode and the cathode of the diode equivalent on this device here. Let's put it onto forward voltage drop again. We're on diode forward voltage drops mode. Now if we look at this now, what have we got? Got 1 volt across it that way. .5, yeah, so there is a kind of diode in there. It's probably a protection diode across the FET you can see there. Ooh. So nothing absolutely short. Nothing absolutely short. Nothing absolutely obvious. I can't see any bad solder. This is the bit squirrel shit, isn't it? That bit there is like not great soldering. Well, I could just go off and if you weren't here watching me, I would just get the soldering iron out, change both devices. But in the interest of helping you to understand or debug, I'm not, you may be fully conversant. I don't want to teach grandmother to suck eggs, but you might find it interesting just to have a quick poke around with the scope and look at the data sheet for these devices, and we can just see what's happening on the scope, on the screen, and then we'll see if you can deduce what's wrong before I tell you what I think is the problem, and then we can go ahead and see if I'm right or not, which I might not be, but you never know. Anyway, so onto the screen, and we'll take it from there. Okay, so here it's okay, so it's set up on the bench. We've got mains coming here from a isolated supply. So in this respect, live and neutral has no meaning really. It's not referenced to the supply ground at all because it's coming through an isolation transformer. And what that allows you to do, if you haven't got an isolated scope input, you can connect your earth clip to the AC 0 volts rail. If you did this with a standard scope, then when you connect the ground terminal you would get a spark or a bang and probably blow the fuse. Okay, so we're running from an isolated supply, and I've got the scope here on the screen, and I've clipped it onto the board. I've soldered a wire on, and we're just going to look at some of the signals that are happening when this thing is turned on, which it is at the moment, so I have to be a bit careful. Alright, so I'll just give you a close-up view of what we got. There it is. Okay, so anyway, let's go over to the scope and have a look at that. So here's the data sheet for the U6513BS. It's in Chinese, but we can work out what's going on. There's the pinout of the chip just here on the screen, and if we slide down we can see the names of the signals. I understand what they are, so I can explain them to you. I'm not bothered translating the data sheet today. And here's a typical application circuit, and I have no reason to believe that what's actually on the board is any or significantly different to this at all. So if we just make that a little bit bigger, we'll just run through the circuit quickly. So there's the reference circuit from the manufacturer. So you can see you've got live and neutral coming in up here on the top left, going through our bridge rectifier. The negative of the bridge rectifier is what we call AC 0 volts typically, and you can see that AC 0 volts is referenced in different places. So distinct from the low voltage sides, which is over here, which is a separate 0 volt symbol, because this is electrically isolated directly from the high voltage side of the input. Clearly you don't want any mains voltage getting onto the secondary side because it would administer a pretty bad electric shock probably. Okay, so here we are. We've got the mains coming in here. Here's our 4.7 microfarad 400 volt capacitor. That's the main reservoir capacitor. Here's the slugging circuit, or the clamping circuit for the transformer primary. We've got a resistor, a small capacitor, and a silicon high-speed diode, which basically arrests the back EMF from the transformer. And every circuit will have one. Very common for these diodes to go short. We know it's not shorted because we've tested it. Then here you've got the 300k resistor going from the B plus line, which is AC B plus, which is about 360 volts at this point here on the top, and it goes through the 300k resistor down through to the reservoir capacitor for the VCC, or VDD they call it, to ground. So that's the 10 microfarad 47 volt electrolytic we looked at on the board. Okay, just there. Now what happens when you turn the power on? AC arrives here, the voltage goes up here, so the AC B plus goes up to 360 volts on the UK mains. This resistor then is a path down to charge this capacitor up, and this will ramp up slowly, probably over the space of 400 or 500 milliseconds, until the chip detects that the voltage at this point is on pin 1, the VDD. That voltage there is up, reaches say maybe 18 volts. Then the chip will kick in and try and start the switch mode power supply, and as it starts it induces a voltage in this winding down here on the left, this winding here, and that winding there is on the primary side, and this one serves two purposes actually. There's the voltage being generated, it goes through the diode, the rectification diode, and then when the power supply is running, these pulses from here go through here, through the diode, are rectified, feed the capacitor, and then supply the actual running current required. Up until the point which this starts to produce power, this thing is just running on the charge that's been stored in the capacitor. All right. So let's just have a look at that voltage now. We're clamped onto here, which is the pin 1 of the switching mode power supply IC. All right. So if we just have a look at that. Right, so we can see what's going on. You can see that, look, it's ramping up. We're on 100 milliseconds per division of time base. So we've got over 500 or 600 milliseconds. It ramps up. If I can just stop that now using the trigger. Okay, so when the time per division is longer than 100 milliseconds, this O1 scope is set to auto mode and it can't lock on. So I'm going to, you can't even put it in single mode by look of it, so I'm going to speed up the time base to 50 milliseconds. All right, okay, so I've frozen it. So that's a one cycle. You can see it was ramping up and discharging and ramping up and discharging, but now we've frozen it, and you can see it's ramping up as that capacitor charges up, and it gets to there. This is the point there where that switch mode power supply tries to kick in, and it kicks in, but the bootstrap supply doesn't come and take over, so the voltage on the capacitor just ramps down again to a point where it can no longer be used and the unit shuts down. Okay, so for some reason this is trying to start up, but it can't, right? So there's nothing coming out of the transformer, or there's a short or an overload. So let's move the probe across slightly. We'll go back to the unit, turn the power off. Most important to remember to turn the power off. And we'll move the connection to another place, which we can have a look at and see what's going on. So it's trying to start up and it can't. Okay, so either the chips are faulty or there's a short somewhere on the system. So I'm going to move this wire here, which is my scope pickup wire, from the reservoir capacitor for the V+. I'm looking for my pot of robot pubes. Where have they gone? Can't wipe my tip. Where the bloody hell are they gone? Oh, there they are. I was wanting to give my tip a quick wipe. No one likes a dirty tip. Okay. And then we're going to solder this onto the top of the resistor, which is the current sensing 820 ohm resistor just here. And we're going to just tack this onto pin 1 of the chip, which is the current sense connection, and see what current it's sensing in the primary of the transformer. Okay, so we've moved the pickup wire to pin, oh, that's the wrong pin. That is the wrong pin. Done that wrongly. Write it down, made a mistake. It should be the current sense connection, which is sensing the voltage across that 0.8 ohm current sensing resistor, which is the current proportional, voltage proportional to the current that's actually flowing in the transformer primary. Okay, so we're on pin 4, current sense. Let's go back to the screen. I'll explain where we are. Right, okay, so we're over here. We're here, pin 4, 0.8 ohm resistor down to AC 0 volts. The FET is inside this area here, if you can imagine it. between pins 5, 6 and here, and the drain of the switching FET goes through that resistor to ground. So whatever current's going through the FET will generate a voltage across that 0.8 ohm resistor. Then if the current is too high, then the voltage is too high, the chip can sense it and shut down the FET before any damage is done, i.e. react to an overcurrent or a short situation. So here's the scope. We're setting up 200 millivolts per division. We've got it running at 50 microseconds per division. And you can see that's the voltage being generated across that resistor as it tries to start up. So every 400 or 500 milliseconds, it's going through this pulse situation where it tries to turn on. It does 4 pulses, but decides, hey, this is not working. There's an overvoltage. And if we scroll down if we go back to the data sheet, which is over here, you can see that if I scroll down to CS, so we're talking about the voltage on this comparator here at the corner, and there'll be a maximum limit at which point the switching PWM is turned off to the output FET. Let's scale that down a bit so you can actually see this. CS, maximum voltage is minus 0.3 to 0.7. That's not the cutoff voltage. Cable max, VCS match. Someone down here will be a CS voltage. DSD, RC, VCS. Okay, there we go. So VCS current sense is 490 to 500 millivolts, 510. This is the indication at which point it will switch. The reference voltage for the comparator, which is looking at that voltage in the across that resistor. So we've got literally we're 200 millivolts per division, and you can see it gets up to 400, 450, and it shuts off. And then the cycle stops and it waits for its reservoir capacitor to charge up again. So that is fairly conclusive that there is an overcurrent situation somewhere. So it's either in the rectifier, there's not much on the secondary side. It could be the transformer, don't forget. You might have a shorted turns on the transformer or burnt out winding. But having said that, it probably isn't that. But who knows what it is. Right, so let's have a look on the input to the rectifier, see what we've got. I know. Let's have a look at this point here. Here we are. Let's have a look at, where should we have a look at? Let's have a look at, yeah, let's have a look at the input to that rectifier diode. Here, at the output of that winding. So the input to the actual rectifier diode, put that on the screen and see what we get. So let's turn our gain down on the scope. Right, power off. Check power off. Right, we're going on the cathode of that rectifier diode. So that will show us the voltage across this winding. This is a transformer winding. There, okay, so let's just turn it on. That's what we've got. We're on 5 volts per division. Can you see the divisions? You can just about, can't you, I think. Let's just make this window a bit bigger for you. That's more like it. So we've got like 7.5 volts peak. The four thing, it starts to conduct into that capacitor and then rings away to 0. So I wonder if that's actually moving the voltage on that capacitor, because that does seem strange actually. There is some power coming out of the transformer, it is trying to start, but it's not reaching enough sufficiently high positive voltage. Remember, it's the positive peaks on those waveforms. Oopsie daisy. It's positive peaks on these waveforms here, so we've got 7 volts. All right, so but it's not actually producing enough oomph before the FET cuts off. And what's happening here is the FET is conducting, the current in the drain of the FET is going too high, and the thing is just shutting off, even mid-cycle probably. So the question is, if we then go back to the diagram again, and we look at the output here to the input to this diode, which is in this case, we haven't got a standard diode. We've got that precision rectification circuit, that lossless diode chip on there. So basically, let's put the scope on the output of the primary of the transformer on the secondary side and see what we get. Turn the power off. So we're going to connect it to the output from the transformer. This is the output, the secondary side, low voltage primary. Okay, so that's on there. Let's see what we're getting out of the transformer, shall we? Right, what you can see there on the screen is the overshoot, because it's rectifying on the negative cycle, so it's only the bit at the bottom of the screen below the 0 volt line we're looking at. So there's no power coming through the transformer. I think it's not good at all. I think it's not driving anywhere near as hard. It's shutting off due to the overcurrent condition. So either we've got a faulty rectifier on the screen now, you can see, or there's something else going on. Can you guess what it might be? I don't think the power supply chip is faulty, but you never know. It might have an internal fault, which we could take it out and change it, swap the chips out. But yeah, I mean, I would just swap the chips out, I think, if you weren't here, just to rule out the ICs, because they can fail in some weird and wonderful ways. But I'm suspecting it's something else. Now, can you think what it might be? Have a guess. Meanwhile, let's get on with changing the chips. So there's the device we're going to change. Get a piece of masking tape and move that lead, stick it down to the bench. Right, I could change this with hot air, but I'm assuming a lot of you guys don't have hot air, so I'm going to do it with the soldering iron, just to show you that it can be done. I'm going to flood the pins on both sides with a bit of leaded solder. If there's unleaded on the board, the leaded solder will form a nice eutectic with the lead-free solder, which has got a higher melting point, as you all know. And as that happens, it makes everything, drops the melting point by about 30 or 40 degrees and makes it much more workable. So a simple method of doing that is to do what I just did. I would normally use hot air, but I'm not today. So heat one side, can you see? Can you see that? And heat the other side, heat this side, pulling all the while. I'm just trying to lift it with the tweezers. As the heat gets into the board, be patient. There we go. And the chip has left the building, so that's how that's done. Now, just wipe your tip. If you keep wiping your tip, you can hoover up that solder. It's just a single connection there. There's no tracking in between that. They've just put a big wide copper pad for those two pins, so they're common anyway. I would use solder braid, yeah, like the blotting paper stuff, but also a clean tip will get you there in the end. He says, without any sort of conviction. Now I'm going to have to use a bit of braid on that, I'm afraid. What you can do is just use a tissue, a wet tissue. But today we're going to do a bit of soaky, because it's the design of this board is not actually lending itself to it. So you can see you've got this massive pad there. Not such a good technique on massive pads. Works well on small pads. There you go. Give it a bit of a scrub. This isn't a high voltage device. If this was a high voltage device, I would clean underneath that chip, but it isn't, so I'm not gonna. Alright. Okay, so where have we got? We got our chips. It's a CY7319. I'm not sure this can actually fix this, but it does seem odd that that voltage is going into there and it has got a connection to ground and nothing is coming out the back side of it, which is, I didn't measure a short on the low voltage DC output side. There may, no, it's not the CY7319, is it? As it happens, we do not. As it happens, we do not. Actually, I will give it a clean. It's looking a bit like, but there's trouble with the 60 yen. It does leave a bit of residue. So, isopropyl alcohol, wife's toothbrush. Give it a bit of a rub. Looking a lot more respectable now. Okay. Drum roll, is this going to work or not? I have my doubts, but at the moment it's the top suspect. Turn the lights off so you can see the whole dreadfulness. Right, power on. Mains applied. Be careful. How much voltage have we got now on our components? No, it's exactly the same. So that was a false diagnosis. Alright, well I'm going to change the power supply chip then, because I think everything else is okay on this board. My only other thought is that it might be, just turn the lights back on. My only other thought that it might be the rectification diode, because it was doing something strange. I wonder if that diode is faulty, because we didn't see a corresponding rise in the bootstrap was starting up. The diode measured out okay though. What do you think? Let's just check that diode again. So this is the bootstrap supply rectification diode. And we saw the waveform was coming in, was correct on this side, didn't we? Well, it's a PCB fault. No, ground's got continuity, the winding's got continuity. The secondary winding, we may have shorted turns on the secondary winding, but it is giving less than 1 ohm, and the primary winding, it's off. The primary winding is probably these two connections here. Oh, that's the bootstrap winding. Okay, well, what I'm thinking at the moment is it may be the transformer. It's either the chip, the switch mode power supply chip, or the transformer. On the primary winding, on the bootstrap winding, we get 0.9 or 0.5 ohms, but on the primary we get 2.7 ohms, which take away the 0.4 on the meters, 2.3 ohms, which is pretty low for a primary winding wind. I wonder if there's shorted turns on the primary winding. We're getting very high currents across this resistor. We know the resistor value is correct. We're getting a very high switching current, which is causing it to shut down, and it's not producing enough flux in the transformer even to supply the bootstrap or kick the bootstrap. Normally, if there's a short in somewhere else in the secondary, you'll see a kick in the bootstrap voltage. We're not seeing that. We're getting the straightforward passive ramp. So as elastics, I think I'm going to change the switch mode chip. It may have an internal fault on it which is causing it to do something strange, but for me, we've changed the actual diode pack. The high efficiency rectifier has been changed. So I wonder if that switching line is connected properly to... Okay, so what is it? We know it's not the diode pack because we've just changed that, although we suspected it. Let's just check the bootstrap power supply winding and feedback winding at 0.9, so that's about 0.7 ohms, and the primary is reading 2.7 ohms, which seems a bit low to me. Actually, with the meter leads taken into account, it'll be about 2.3, 2.4, and that seems a little bit on the low side. So we may have a short on the primary. So instead of charging up the magnetic field on the transformer, it's just shorting a resistive short and overloading the input. The current goes too high and the FET turns off and everything dies. So I was poking around in their drawers for about half an hour, and I decided the only way to really confirm the diagnosis is to change the PWM chip. One final ditch attempt, but I think it's okay. It seems to be behaving normally, so yeah, it's a last ditch attempt, in which case the diagnosis will be confirmed. Right, so same old procedure, same old. Get some EN60 flux core solder wire, dilute the tin Okay, here we go. What do you think, boys? Do you think we're going to have a solution here, or stay-mo, say-mo? No, exactly the same. Worse, in fact. I've got some voltage coming in here, haven't we? AC 0 volts and there. 276. Let's give it a bit of a boost. No, it's doing exactly the same thing there. So we know it's not that, it's not that. We haven't actually replaced this diode, even though it's metering okay. But I was kind of odd that this Okay, chaps, well, we've exhausted every possibility. We've changed both of the chips, we've checked all the circuitry, and upon reflection, it's got to be the transformer. Look at the size of this thing, it's tiny. If I just show you a... Have I got one handy? I haven't got one handy. I had one earlier, but I think I might have lost it. Oh, here we are. Yeah, so here's an IKEA 2 amps, but it's just not 2.4, this is 2 amp, okay? So that's a 2 amp IKEA. Now look at the extra electronics in that thing. It's got the slot there for the isolation from between the high voltage side and the low voltage DC side. You've got a separate fuse here, got a fuse, got a inrush limiting resistor, you've got a varistor 371K, is it? 471K, 275 volt AC variable resistor, which soaks up any charges, which transients that come down the line. You've got loads of big capacitors. You've got a stonking great transformer. This is a 2 amp power supply, don't forget. Look at the size of that transformer versus that transformer. So is it any surprise the transformer's blown up? 2 amp, 2.4 amps, 2 amp, 2.4 amps. Look at the size of it. And you can see the high voltage lines have been put out, or the low voltage lines have been stretched out away from the high voltage. There's this big gap down here to stop anything from the main side conducting or flashing over onto the low voltage side, which your children are exposed to, right? So that's a 2 amp IKEA one with all the necessary requirements, and I think this is what you would need to meet UL. All right, you've got filters, you've got chokes in there. Look at the difference in components. Look, yeah, so absolute minimalist design, not UL approved. It's just been rubber stamped. Trouble with UL, sorry, not UL, I'm talking about Underwriters Laboratory. Painful that was when I used to have to do those products. No, CE approved, not CE approved. The trouble with CE approval, you can self-certify, so you have a constructor's file that says, I think it's CE approved because whatever, but clearly this isn't, and it's probably unsafe too, probably. I shall test it at some point. Anyway, Tiddly transformer, 2 amp transformer, 2.4 amp transformer, make your own mind up as to which uses 2.4 amps a year or two. Give this one a good load. I mean, we don't know if it actually produces 2.4 amps or not. That's the question. It might just be rated 2.4 on the label, but I only produce one. I don't know. So what I'm going to do now is I'm going to order a new one of these from Amazon, take it apart and see if they're shipping the same old crap, and if they are, we'll see what we can do about it, because not good enough for a 20 quid product, is it really? It's just a waste. It's going to end up in the skip. It's just... Anyway, thanks for watching. If you can subscribe to the titty button down there. I'm sorry it's been a bit long and drawn out, but that's repairs for you. Sometimes it's easy, sometimes it's not, sometimes you succeed, sometimes you don't.